right. So looking at these problems, so if we we'll start by quickly reviewing what it means to be continuous. All right. So in order for something to be continuous, so remember, in order for a function to be continuous, a couple things need to be true. All right. First of all, f of x needs to be defined at c. Okay. That means if you plug in whatever number you plug in for x, it cannot give you, does not exist or undefined. All right. Second, the limit as x approaches c from the left and from the right needs to be equal. Okay. Therefore, the limit needs to exist. So the left-hand limit and the right-hand limit need to be equal. The limit, so that makes the limit exist. Now, the final thing that needs to be true is that in order for this function to be continuous at x equals c, whatever that value is for the limit has to equal the function value. Okay? So we will start by looking at number 2. All right, it says, all right, f of x is equal to square root of x plus 5. We're looking at x equals 8. All right. So step 1, we want to make sure that this function is defined at x equals 8. So how do we do that? We plug 8 in. So f of 8 is equal to square root of 8 plus 5, which is equal to the square root of 13. Okay. Now, square root of 13 is a little bit, that's going to be a decimal. All right. So that's okay. Now, so actually, let's do this. We are going to now, personally, if I ask you guys this, all right, I expect you to know what the square root of 8 or 13 looks like, or the square root of x plus 5 looks like eventually. But so if we look at this, I expect you guys to be able to find the limits. You can use your calculator instead of having to draw out a table. All right, so I believe I told you guys to make sure that your guys is all close to. Well, I think that's what I did. I told you guys to set your table to 0.001. Does that sound familiar? I think I told you guys to all set your table chart. So you go second window. So yeah, you calculate second window. All right. And then you're going to set your table start at all these changes. So since we're looking at x equals 8 in this problem, we're going to go ahead and make that 8. And your table start, just for the rest of this class, you're just going to keep your table at 0.001. All right. So then we're going to go y equals. If you have anything there, go ahead and clear it out by hitting clear. And you have the square root of x plus 5. We're going to graph it. All right. So once you have it graphed, what we can do is we're going to hit the second table or second graph. We're going to bring up the table, and you guys will see right here coming from the left and coming from the right. All right. So as you can see, the left-hand limit is equal to 3.605. So obviously it's getting really close to right here, 3.606. All right. So it's getting really close to 3.605 and 3.606. Now we said square root of 13. So you have to go back and look because what square root of 13 is. Second, square button, 13 is 3.606. All right. So we go back to our table and we see, okay, it's approaching 3.606. And actually, your guys' advice says something a little different than mine. We do something real quick. So, let me do square root of 13. Square root of 13, 3.60555125. So I'm going to look at my table again. 3.6053, 3.6054, 3.6056, 3.6057. So notice it's getting closer. It goes 5, 5, 1, 5, 3, 5, 4, 5, and then it goes to 5, 6. Same thing here. It's going 8, 7. It's getting closer to that 3.6065, which is, if you look at it, square root of 13. It just is rounded in the table. All right. So the conclusion that we can draw there is that the left hand limit and the right hand limit was equal to 3.60 whatever, which is the square root of 13. So we know that the limit as x approaches 8 from the right and from the left of f of x is equal to square root of 13. Alright. So since f of x, or since f of 8 is equal to the limit as x approaches 8 of f of x, since these two are equal, that tells us that this is continuous there. Alright, that's continuous. And at that point you're done. You've proven that f of 8 exists, you've proven that the limit exists, and you've proven that they're equal. Okay? Number 4. Okay, so number 4 here, we are looking at the problem. X squared minus 5, so we have h of x is equal to x squared minus 25 divided by x plus 5. Okay, now, and we are looking at the values at x equals -5 and x equals 5. So, x equals -5, x equals 5. Okay, so first of all, what's the first step we want to do? Well, we're going to plug both those in. We're going to see if the first thing we're checking is this function defined? If it's not defined, that means it does not exist. And if the function does not exist, if it doesn't have a function value there, definitely not continuous. So, if I plug in -5, I'm going to have f of -5. I'm going to get -5 squared minus 25 divided by -5 plus 5. It's going to give me 0 divided by 0, which is impossible. Okay, so what that tells me is f of -5 does not exist. That implies that it is not continuous. And I thought I said this, maybe I didn't. If you ever plug something in and you get 0 divided by 0, okay, that means that you have a hole. It is a removable discontinuity. So, again, if you ever plug in a number and you get 0 divided by 0, it is a hole. All right, so this f of -5, this is a hole, and that's called a removable discontinuity. Okay, so that's x equals -5. Now, we'll look at f of 5. f of 5 gives me 5 squared minus 25 divided by 5 plus 5 is equal to 0 over 10. That's just equal, that's 0. 0, 10, 0. So this right here at x equals 5, that means that this is continuous. X equals 0, therefore, continuous at x equals 5. Because, actually, I'm jumping to conclusions. Alright. I'm not going to erase that because I'm pretty sure it is continuous. But what we know right here is that the function value is equal to 0. Now we have to prove that the limit is equal to 0 there. So we want to look at the graph. So if you look at the graph, we're going to type the calculator. We're going to graph x squared, let's put it in parentheses, x squared minus 25 divided by x plus 5. Alright, and it's graph. Let's see what that looks like. There's my graph. And we want to see, we're looking at, okay, so we're looking at the x value, x equals 5. So we want to go second window, because we don't want to have to scroll up like 10,000 different numbers. Alright, so we're going to put this number 5, that's the number we're looking at. And we're going to get second graph, look at the table. So if we look at this, and we decide, alright, what is coming from the left? This is getting really close to 0. This is getting really close to 0. And then eventually gets to 0. So what we can say, alright, to finish our conclusion, is that the limit as x approaches 5, and okay, notice here, alright, the limit as x approaches 5 exists because the left-hand side and the right-hand side are going to the same thing, alright? So, limit as x approaches 5 of f of x is equal to 0. So, since f of 5 and the limit as x approaches 5 are equal, we can say it's continuous x equals 5. That makes sense? Here's a kind of like almost like a general kind of shortcut / cheat. If the function value exists, all right, and it's not a piecewise function, you're probably good to assume that it's continuous. But just to be on the safe side, you want to check it. So that's 4 here, 6, 8, and 10. I want to try to get you guys to take quiz no later than 2:45, but we'll see.
2:45.
1:45. Now I want to celebrate my birthday, but I usually get that school. So, that's perfect. Right? 2 minus x. 2 plus x. And we're looking at x equals -2. So, first thing we want to do is what? Plug them in. So, let's plug in that g of -2 first. We're going to have 2 minus -2 divided by -2 plus, nope, divided by 2 plus -2. That's going to be equal to 4 divided by 0. That's not doable. 4 divided by 0, that's under 5. So, here's, first of all, jump discontinuities only occur with piecewise functions. Alright? Here, this is not a whole, because a whole would be 0 divided by 0. This would be what we call an infinite discontinuity. Alright? Okay, and we're gonna look at this later. So we know that if it is not contiguous, at x equals -2. It's an infinite discontinuity. It's not, and that's a type of non-removable. Okay, non-removable. Now, we're gonna check g of 2. That's going to be equal to 2 minus 2 over 2 plus 2, which is equal to 0 over 4, which is equal to 0. So g of 2 equals 0. Okay, so that's good. Now, can't jump the gun here, but that's good. Now we just need to check to see if the limit exists, and if it does it equal 0? So, again, we're going to go graph it. We'll graph it with a new calculator sign. Alright, so we're going to go to y equals, our equation is, again, whenever you have something like this, you need to put the numerator in parentheses and the denominator in parentheses. So 2, so parentheses 2 minus x divided by parentheses 2 plus x. Alright, so far we said it has an infinite discontinuity. Infinite discontinuity at -2, and we said that it is g of 2 is actually equal, so we know it has a function value. So in order to check to see if this function value, or to see if this function is continuous here, you have to look at the table. Now we're starting at 2 this time, so we're going to go second window. Instead of table start 4.997, whatever you're at, we're at 2. Then you go to second graph. Alright, we look at this and we see, okay, so see, did you guys say the same thing as mine? This e -4? That just means really, really small. Alright, so it's really, really small, getting a little bit bigger, getting a little bit bigger, it's equal to 0. Here it's getting really small, getting small. That's just means it's 0. Alright, so obviously it's approaching 0. Alright, now, so we can draw a conclusion here. Since the limit of this is equal to, alright, so the limit as x approaches 2 of g of x is equal to 0. So since these are both equal to 0, continuous. Alright. Now I do want to look at -2. So we're going to look at g of -2 on the graph. So first of all, you can see right here, there is a break in the graph at -2, right? Right there, just sort of break it apart, all the way up and down. And what you notice is, if you were to go to look at the table, second window, and you go to the table start -2, and we go to the table by hitting the second graph. First of all, you'll notice that -2 says error. And I also want you to notice this. So even if somehow I had a value that existed, notice the left side limit goes -1,334, -2,001, -4,001, error. And then on the right hand side goes 1,332.3, 1,999, 3,999. Is the right hand side approaching the same thing as the left hand side? No. The left hand side is it's going off the negative infinity. It's just blasting off, going down really fast. Here, this is going up to 1,000 or 4,000. Positive infinity. Keep going up to positive infinity. Right? You guys don't need to do this, but if I did, I can go second. I can go 0.00001. What you'll see is, really fast. It's here than 99,000. Alright, it says -2, but it's not really -2. It's like -2.0000001. Alright, so that's that. So questions about why that is, why that one's the way it is. Well, making a little more sense. What? Yeah,
I feel like I'm at halfway.
I let you back those. Alright. So let's look at number 8. Number 8 says h of x is equal to x times x minus 6 divided by x cubed. We're looking at x equals 0, x equals 6. Okay, already we can see this initially when you plug x equals 0, can we not? It's going to be, well, yes. So, it's not automatically a whole, but what we see automatically is just by plugging 0 in, we have something divided by 0. So, we have h of 0, that's equal to 0 times 0 minus 6, divided by 0 cubed, which is equal to 0 divided by 0. So, x equals 0 is a what? Whole. Alright? It is a removable discontinuity. It is discontinuous. Okay. Now we have to plug 6 in. We're going to get h of 6. It's going to be 6 times 6 minus 6 divided by 6 cubed. To be honest, I don't know what 6 cubed is off the top of my head. So this is 216. This is going to be 0 divided by 216. Should be 0. So the function value exists. Again, we actually, let's look at the graph here. So we have y equals, so we got parentheses x, parentheses x minus 6, parentheses divided by x third. There. Got it? And so you can see others could be why this is looking like a asymptote there. I mean, negative 30. You got it? Negative 0. I'm still gonna roll it because there's a hole there. Remove the discontinuity. Oh. Not remove the discontinuity. So this now, so bear with me here. Okay, so there's a hole. I'm just going to think about this one. I think there actually might be a hole and a but I'm going to come back and think about this one. That's a star. It is definitely discontinuous. But we can look at 6. We'll just go with it. Not really want to look at it right now because that's kind of annoying me. We know that the limit as x approaches 6 for this one is going to be for h of x is equal to 0. So since they're equal to 0, again, since the limit and the function value are equal together, this is a continuous function. Okay? So Number 10 is a piecewise function. Alright? Yes, what type of discontinuity is it gonna have? Want to take a guess? What type of function is this? Piecewise function.
I think you're having, for one.
Last one, right? This is number 10. So number 10, piecewise functions are going to give you jump discontinuities. Okay? So if there's a discontinuity here, it's probably going to be a jump discontinuity. We'll have to double check though. You have f of x is equal to x squared minus 1 when x is greater than negative 2, and x minus 5 when x is less than or equal to negative 2. Alright, so you have to do two things here. First of all, you have to see if the function value exists. Okay? Does it exist? Well, which of these are we going to plug negative 2 into? The top and bottom. Bottom. Good. So it's going to be f of negative 2 is going to be equal to negative 2 minus 5. Equal to negative 7. So f of negative 2 exists. Alright? So now we need to see if the limit exists. So we're not going to look at the graph of this one. We're going to look at the left-hand limit and the right-hand limit. So look at the left-hand and right-hand limit, you just plug negative 2 into each of these. So if I plug negative 2 in here, I'm going to get the limit as x approaches negative 2 from the left, alright, is going to be, I'm going to plug into this one, so it's going to be f of x, so it's going to be equal to negative 2 squared minus 1, which is going to be equal to 3. The limit as x approaches 2 to the right of f of x is equal to negative 2 minus 5. We've already done that one. Negative 7. Is the left hand and right hand limit the same? So, what does that tell us about the overall limit? The left hand and right hand limit are not the same. The function is not going to one specific value, so the limit would be not exist, does not exist. Alright? So the limit as x approaches 2 does not exist because the left hand and right hand limits go 2 different places. Does not exist equal negative 7? No. So that means that this is not continuous or discontinuous. And since the left hand and right hand limits are different, it's a jump discontinuity. And let's clarify. Since they're different and not equal to negative or positive infinity, since they actually are equal to numbers, it's a jump discontinuity. All right. Questions about that? All right.